Okay, so let's start today's session. So hi everyone, good afternoon. I'm Papia Panda and I'm going to share my screen so that you all people can see that. Just a minute. Can anyone confirm that it is visible or not?
Yes, it is visible.
Okay.
It's visible.
Okay, fine. So yeah, just wait. Okay. So yeah, so people are coming still. Okay, putting that on. Okay, just okay, so let's start. So basically this is the course name Nuclear and Particle Physics, as you already knows that one. So the course instructor is Professor Paulos and I am Papia, who is the PMRF NPTEL teaching assistant. So today, not only today, that this whole the course. So in that whole course, what I will do, I will just discuss something about the previous year question assignments. Okay, not this year question assignment obviously. So I will just discuss about the previous year question assignment, and it will be like discuss means like question will be there and answer will be there, something like that. And the whole course is obviously of 12 weeks, so there will be 2 hours per week, that means 24 hours as a whole for the discussion of the previous year assignment. Okay, so yeah, I think from the next class I will do that one, that automatically admit thing. Okay, so this is the first class. So in the first class, what I will do, basically I will do like assignment 0, week 0 assignment, which is obviously given in the previous year course. And also after that, what I will do, I will do the week 1 assignment if there will be some time left. So basically first of all we will do about the week 0 assignment, which is assignment 0, and then we will talk about week 1 assignment, week 1 assignment, previous year week 1 assignment course. Okay, so let's start. Like I think sorry to disturb all of you, that okay. So this is the first question as per the previous year assignment of week 0. So I think you have already attended the first class of Professor Paulos about the nuclear and particle physics. In that course he has discussed about the very basic of the nuclear and particle physics courses, like what it will be discussed in the following weeks, and what will be the main syllabus for that, and very basic things of nuclear and particle physics he has already discussed. So on the basis of that questions, there is some question, on the basic of that lecture, there are some questions which is in the week 0 course. So what is the first question? You can see that the first question is like 2 particles of spin half and 3/2 are combined to form a bound state. Okay, one more thing, I will just tell you one thing, that whenever you have some doubt, you can just ask me anytime, like in between the question also you can ask me anytime. Just unmute yourself, and after that you can you can ask me the question. Okay, so basically this whole course is not only the not only from me the discussion will be, it will be from your side also. It will be an interactive course, so that it will be beneficial for all of you. Okay, yeah. So let's start the first question. In the first question, what is the question? The question is 2 particles of spin half and spin 3/2 are combined to form a bound state. Which of the following which of the following is possible value of the total angular momentum of the combined state? That is the question. So, and there are 4 options for that. It is a very simple question, that's why it is a multiple choice question. So you have to click any of them, which will be the correct answer. So first of all, I am just going to discuss about the first question so that it will be beneficial for all of you. So basically the question is like there is 2 particles, one is spin half and another one is spin 3/2. So like let's say I am writing here S1 equals to half and S2 equals to 3/2. So these 2 are combined to make a bound state. So they are asking about the which of the following is the possible value of the total angular momentum of the combined state. If you have some idea about the quantum mechanics, very little bit of that also, then you can have that as a whole the combined total angular momentum can have the value mod of S1 minus S2 to mod of S1 plus S2 in the step of 1. So this is the main this is the main take off message from that question. So what is the answer right now? Like basically they are asking for the capital S. So capital S will be what? It have the value mod of S1 minus S2 to mod of S1 plus S2 in steps of 1. So if I just calculate a little bit, then you can see that the capital S can have the value. Let's say I have a mod of S1 minus S2. So why it is a mod? That means we don't want minus value. That means let's say half minus 3/2. This is the mod of half minus 3/2 will be what? It is nothing but you can see that it is the 1 value. And then mod of, obviously mod there is nothing with that mod for that plus value. Then what will be the value of 2? What if the value of this is 2? That means the S value can have 1 to 2 in the step of 1. Obviously in between 1 and 2 there is nothing in step of 1. That means the S can have 2 values, 1 or 2. So the question as it is asking about the total angular momentum of the combined state, the total angular momentum of the combined state will be either 1 or 0, or 2, because you can see that I have written here half minus 3/2 mod equals to 1 and half plus 3/2 is 2, and it should be value, the capital S should lies between 1 and 2 in steps of 1. As there is nothing in between that 1 and 2 in step of 1, then we can have a S value as 1 and 2. But here in that option you can see that there is no 2 option. That means the options are here half, 3/2, 0 and 1. So obviously the correct answer will be 1, because capital S can have 2 values, 1 and 2, but as there is only one value as 1, that means the correct answer will be D. Okay. So this is the first question. I hope all of you understand that one. It's a very simple question. So I have given the answer of that also. Okay, one more thing I would like to say, that this lecture is right now recording. It is recording and it will be shared in one YouTube video, YouTube channel, and it will be shared to all of you. Then so just tell to your friends that even if he or she will not be able to will not be able to join in that live session, he or she can see after the finishing of the lecture when it will be uploaded in the YouTube channel. So, and I think from the NPTEL view, they will share with the YouTube channel with all of you, so that you can see later also. And one more thing is that I can also share that slides whatever I have made for that lectures and all. So that will be also accessible by you after the lecture. So you can see after the lecture also that what will be the result and what is the answer for that questions. Okay. So coming to the second one, I hope the question number 1 is understandable by all of you. It's a very simple question, that S1 and S2 is there. So the combined total angular momentum will be mod of S1 minus S2 to mod of S1 plus S2 in steps of 1. So as there are two values 1 and 2, that means my answer will be 1 and 2. So but as in the question there is only one option as 1, that means our correct answer will be D, which is 1. Now coming to the second question. So in that second question what it is saying, the second question is a doubly ionized lithium atom is in an excited state of energy minus 13.6 electron volt. Okay, so it emits a photon of energy 17 electron volt to come down to a lower energy state. What is the final energy level? So like what they are asking here, basically you can see here, like let's say this is the ground state. Okay, so in that ground, this is the ground state. So in that ground state, the excite and this is the nth state. Let's say it is the nth state. So the question is like what is the value of n, so that from going to n to 0th state the photon will have the energy of 17 electron volt. That is the question, and you have to tell what is the value of n here. And the values is like they have given that the doubly ionized lithium ion is in excited state of minus 13.6 electron volt, that and then it emits a 17 electron volt photon to come down to a lower energy state. And what is the final energy level, I mean what is the final energy level for that? So there is a very simple one, like you can see that, like obviously in quantum mechanics the En is like E0 into z square by n square. This is the expression for that En. And what is the E0 here? E0, I mean Z, okay, Z is the atomic number of that atom, and E0 is the ground state energy of the hydrogen atom. So here also you can see that it is given that ground state energy of hydrogen atom is minus 13.6 electron volt. So if I put all the things here, then and also what is En? En is the energy of that nth state. But what was showing as a 17 eV? 17 eV is the difference between these two states. That means if I write here 17, which is nothing but equals to the difference of two states. What are the two states? One is the ground state up to which it is coming, and from which it is coming, that is the second one. So you can see here that minus 13.6 in that question it is showing, it is asking that lithium atom is coming down on minus 13.6 electron volt, and from which minus 13.6 into 3 square by n square. So that's why there are two states difference, which is nothing but 17 electron volt. And what is the value of these two states? One is minus 13.6 and another one is what? E0 is minus 13.6 and then Z square by n square. For lithium, we all know that hydrogen, helium, lithium, that means it has Z equals to 3 value. So that means 3 square divided by n square. This is the expression. So if I calculate a little bit on that expression number 1, we can see that n value is 2. That means that n equals to 2, which is first excited state. This will be the actual answer from where, what is the final energy level. Here it is coming with the a release of 17 electron volt, a photon of energy. So this is the question number 2, and if you can see that it is a very simple expression, that En equals to E0 into Z square by n square. This is E0 and then Z square by n square. So if I put the values of E0, Z and En is the 17 is the not exactly En, it is delta En. So if I put the delta En value and then if I am just going to subtract that one from minus 13.6, then it will give us a value of n equals to 0, n equals to 2. So that the correct answer will be B, that is n equals to 2, first excited state. So after that there is a question number 3. Question number 3 is a very simple one, which is a force reason for the nuclear stability. Okay, so as we all know, there are four forces in our nature. First one is, as I already mentioned here, all of them. First one is gravitational force, then electromagnetic force, weak nuclear force and strong nuclear force. Okay, so I just want to go through a little bit about each of the forces. What will do with the gravitational force? Gravitational force is doing, I mean, gravitational force is nothing but for the big scale forces, like one big mass and another big mass. So the force between these two big masses is governed by the gravitational force mainly. And you all know that in all over the universe, gravitational force is present. Now coming to the electromagnetic force. For the electromagnetic force, what will be the in which case electromagnetic forces is started? It is like it is present in for the charged particles. Like let's say there is a one charged particle and another charged particle. The interaction between the charged particle can be governed by electromagnetic forces. Now coming to the weak nuclear force. In that weak nuclear force, this is like it's basically weak nuclear by name obviously, but it is not that much weaker than gravitational force. Gravitational force is the weakest force among the four one. So the weak nuclear force is basically responsible for the beta decay. Okay, so where neutron and proton is going, I mean in that neutron it is going for the proton, and like we are just having, let's say, positron, and then there is a neutrino. So antineutrino. Yes, antineutrino. So that type of interaction is like a beta decay. It is inverse beta decay basically. So in that beta decay, this is like this one, n plus nu e. So in that beta decay process, we can have weak nuclear force. Like beta decay is obviously governed by the weak nuclear force. But what is strong nuclear force? You can see that inside the nucleus there is a very strong stability. That means which is known as nuclear stability. So how nucleus is stable? The nucleus is stable by the strong nuclear force, and it is only useful for the someone is doing something. Okay. So the strong nuclear force is the main reason for the stability in the nucleus. Inside, you all know that inside the nucleus, what is there? Inside the nucleus, there is neutron and there is proton. So the attraction between these nucleons, these are known as nucleons. So the attraction between these nucleons are governed by the strong nuclear force. So strong nuclear force. Nuclear force. So what is the, I mean what is the question here? Which force is the reason for nuclear stability? The answer will be strong nuclear force. This is this one. It's a very simple one. So I have explained that one also. Among four interaction forces, strong nuclear force is the strongest one, which is also responsible for nuclear stability. That means the correct answer will be strong nuclear force is the reason for the nuclear stability. Okay, so now coming to the fourth question. So in that fourth question, so there is a little bit nuclear and particle physics touch is there. That means we have to use some of the expression of the nuclear and particle physics. So the question is estimate the radius of the nucleus. The radius of the nucleus we have to know for what? For one nucleus which is P1531. So in that P1531 we have to know the what will be the radius of that nucleus, and it should be in Fermi unit, and it should be given by up to 3 decimal place. So this is the question. So in that question, what is given here? They are asking about the one nucleus which is P1531. So I would just going to recall a little bit about that atomic structure and that atomic configuration of that nucleus. So what it is thus means that P1531 means my proton number, okay. Okay, so my proton number is nothing but 15, and my atomic number like A, which is 31, and okay, proton number is Z, and then neutron number is A minus Z, which is 31 minus 15, 16. So this is the notation for that. With the help of this notation we can have that much information, that is a nucleus which has proton number 15, neutron number 16 and atomic number 31. This is the information we are getting from that notation. Now they are asking for the radius of that nucleus. So there is an expression for that radius of the nucleus calculation, that r equals to r0 a to the power 1 by 3. I have written here, yes, r equals to r0 a to the power 1 by 3. As I already told that a is atomic number. Okay, so if I put here number, and what is r0? r0, oh yes, sorry, mass number, sorry, I mean mass number is atomic number, mass number, yeah, I mean mass number is, yes, mass number is A. I mean atomic number means Z1, right? Sorry, someone mentioned me that one. Okay, so A is that one. So A is mass number. Okay, yes. So here what is R0? R0 is the average nuclear radius. So R0 is 1.3 into 10 to the power minus 15 meter. And yeah, what is Fermi? As in that question it is mentioned that I mean the unit should be in Fermi. So 1 Fermi is nothing but 10 to the power minus 15 meter. So if I write here R0 equals to 1.3 into 10 to the power minus 15 meter, then it is nothing but R0 equals to 1.3 Fermi, right? Fermi. So if I just put that value in that R0 expression, and we have A equals to, what was that A? 31, yes. So the A is 31. So if I put all the expressions here, then we can have a number as like 4.084 Fermi. So the correct answer will be 4.084 Fermi, and it should be in Fermi unit, and it has already mentioned something more, yeah, in Fermi up to 3 decimal place. So that's why we have written like 4.084, something like that, because 0.084, this is the 3 decimal place. So that's why we have written as 4.084 Fermi. So this is the main expression, and we are just going to calculate that one with the help of A and R0 value. So now we can have the radius of that nucleus P1531 as 4.084 Fermi. Okay, so this is a very simple one, that if you just put the expression and the value of that terms, then you can get the result of R. Now coming to the fifth question. So in that fifth question, okay, it is a little bit tricky, not that much tricky, but it's a little bit tricky. So in that question, what is asking, the mass of proton and neutron are 938.27 MeV and 939.56 MeV respectively. It is already given. That means proton mass and neutron mass are already given. Find the binding energy of fluorine 919. As I already told you that F919 means what? It has A equals to 19, Z equals to 9, and N equals to A minus Z. That means 19 minus 9, which is nothing but 10. Okay, so this is the expression. I mean, this is the full information which I can get from that notation. Now find the binding energy of fluorine given its mass equal to 18.998403 U, and where U is atomic mass unit. So 1 U is 931.5 MeV, and give your answer in MeV up to 2 decimal place, as they have already mentioned. So we have to calculate up to 2 decimal place at least. Okay, so for that I just want to need the binding energy expression, and after, in that binding energy expression I should put all the informations whatever given in that question. Then I can get the binding energy calculation value of that fluorine. So for to do that, I have already mentioned here, mass of fluorine is this one, like as it is mentioned here. You can see that 18.998403. So if I write here, then this mass corresponds to MeV, because in that expression, in that question they are asking for the answer in MeV. So we have to convert all the U unit, that means atomic mass unit, to the MeV unit. As it is given in U, that means our first task is to convert that U to MeV. So yeah, whatever we have done, the like 18.998403 into 931.5 MeV, then that will give us one expression, I mean one value is 17697.012 MeV. Now coming to the another information, whatever they have given, that mass of proton is this one, mass of neutron is this one. So as these terms, I mean this mass of proton, mass of neutron is already given in MeV, so we don't need to convert anything on that. Now for as I already mentioned that for fluorine 919, the number of proton is 9, number of neutron is 10, and yeah, here you can write here that A equals to 19. Therefore the binding energy, what is the binding energy? Binding energy is nothing but the difference between the mass number and the nuclear, I mean whatever nucleon number. So nucleon mass. So nucleon mass is what? Nucleon mass means like here how many nucleons are there? 9 protons are there and 10 neutrons are there. So each proton have a mass as 938.27 MeV. That means as a whole the proton mass is present inside of that nucleus is 9 into 938.27 MeV, right? And what is the number of neutron? The number of neutron is 10, and each neutron has a mass of 939.56 MeV. That means the total neutron mass is 939.56 into 10. So as a whole, what is the nucleon mass on that nucleus? 9 into 938.27 plus 10 into 939.57. This is the nucleon mass. And what is the mass of that fluorine? Is like 17697.012 MeV. So we have to subtract this one to get the binding energy of that fluorine. So if I just subtract this one, then it will give us 143.018 MeV. So as okay. Yeah. So okay. Just a minute. So this is the expression for that binding energy, and we can get the answer as 143.018 MeV. But in that expression it is showing, it was asking that you have to place that answer in MeV and up to 2 decimal place. Then we can simply write that 143.02 MeV, because at it is 18, so that means it will give us 2 value. So this is the answer of that question. So as a whole, these are the like week 0 assignment 0 questions, and not only that one, last 2 questions whatever I have mentioned here, like 4th question and 5th question, these 2 were coming from the first assignment, I mean the week 1 assignment for the previous year obviously. So I am just going to recall that first one also, because it's only half an hour. So this is the first year assignment. I will just tell you. First week assignment. Yes, this is the first week assignment. In that first week assignment, you can see that the first 2 questions we have already discussed. The first one is that radius of the nucleus, and then the second one is the binding energy of, okay, there is there is another binding energy. That one was fluorine. Oh. Yes, this one we have already discussed, that fluorine 919, it is already discussed in the previous slide. But we have another question in that week 1 session. The question is evaluate the binding energy, I mean the same term we are going to calculate with a different expression. So this expression is, I will tell you what is the expression will be used here, but just let me first introduce the question. Evaluate the binding energy of nickel 2860. So here as usual I can write here, if I just see that one, then I can write quickly that it is A equals to 60, Z equals to 28, and N equals to, what will be the value? A minus Z. That means 60 minus 28. Then it is like 2, then 5, 3, 32. Okay, so this information I already have with the help of that notation nickel 2860. So we have to calculate the binding energy for that nucleus, and we have to use the expression for binding energy in terms of A and Z. It is the question, and they have mentioned some values here. What are the values? The values like the coefficients of different terms are AV is that, I mean AV has 15.6 MeV, AS is that much, AC is that much, A asymmetric is that much, and AP is that much. So what are basically these things? If if all of you knows about the semi-empirical mass formula, then we can have the binding energy expression from that equation only. So I have already mentioned here, this is the semi-empirical mass formula, this one. Expression number 1 is nothing but the semi-empirical mass formula from which we can have the binding energy expression. So you can see that in the left hand side the EB is the binding energy, and in right hand side there are something which is a function of A and Z. Nothing more than that, only A and Z are there, and there are some coefficient on that. So this is the expression for binding energy, and in that question all the coefficients are already given. That means AV value is given, AS given, AC given, A asymmetry given, and AP given. So AV is for the volume term, AS is for surface term, AC is for Coulomb energy term, and A asymmetry is for the asymmetry term. Okay. Now AP is for the pairing term. These terms are coming, these terms are coming to calculate EB, and the EB is nothing but that type of expression. So like what we will do, we have already known what is the value of A, what is the value of Z for nickel 2860. Then if I put all the values here, that has gone there. Okay, that is nothing but 34 into 60 to the power minus 34, 3 by 4. So if I put all the values here, then we can have a little bit like that value, 534.84 MeV. And I think the question has mentioned as MeV. No, they did not mention anything about the MeV or unit like thing. But still, like if we want, then we can put it in MeV, as all the terms are in MeV. So that means we can put this expression of the answer of the binding energy in MeV. So the correct answer will be 534.84 MeV. Like just putting all the values here. With the value of A and Z, and then AV, AS, AC, A asymmetry, AP, and all. So yeah, that is the second question for that first week. Now, as I already mentioned in the third question in the previous slide, so we will skip that. So in that question we can see semi-empirical mass formula in a little bit more detail. Okay. So what is the question here? The question is find the most stable isotope among the following. So there are 4 isotopes here of the sulfur. Sulfur has 4 isotopes mainly. So what are the isotopes here? S1635, S1636, S1637, S1638. These 4 are there in that sulfur isotope. So they are asking that which one will be the most stable isotope among the following. This one, or this one, or this one, or this one. So most stable isotope. Okay. So most stable isotope means what? The isotope for which binding energy per nucleon is the largest will be the most stable isotope. That is the main important thing in that question, that binding energy per nucleon. Okay. So in which isotope binding energy per nucleon is the largest one will be the most stable isotope. So for that we have to calculate EB for each and every isotope. So what we will just do, like I have already given that EB expression. EB expression was nothing but AV into A, then AS into A to the power 2 by 3, then like AC into Z minus 1 into Z by A to the power 1 by 3, and then A asymmetry into Z minus A minus 2Z whole square by A, and then AP capital A to the power minus 3 by 4. So this type of expression were there. So if I just calculate each and everything, like I have already mentioned here the expression again. So if I just put all the values here and then putting the values of s, let's say we are dealing with the first one, s 1635. That means z is 16 and then a is 35, and then obviously the n is like 35 minus n is a minus z, which is what is the answer? 59, 19. So putting the values for this one, as for okay, one more thing is that AP value, we have to know what will be the AP value here. So if there is some conditions for the pairing term, so what is the condition for the pairing values? The pairing value has a significant value for different nucleus. That means if A is odd, then AP will be 0. Okay. Now if A is even means there can be two options, right? One is like n is even, z is even. Let's say the answer, the example for that case is like 6, 6. So that means what is the 6? Oxygen. 6, 12. So for that you can see that, sorry, it is carbon. You have to tell me, you did not tell anything. So this is carbon. So for oxygen also it is like 8, 16. So 8, 16 means like 8 is even, n is even and z is also even. So in that case the AP will be positive 1. Like positive 34. Like this one is plus 34. Okay. And the another option can be like B. B is nothing but A is odd and Z is odd. That can also give as A is even, right? Because why? Like let's say this is 7, this is 7. So these two are odd, nothing but nitrogen. Nitrogen 7, 14. But you can see that the 14, that is A value, is giving as a even value. So for that, what will be the AP value? The value will be like minus 34. MeV. So, but here in that case of S1635, you can see that A is 35. That means A is odd. That means obviously AP will be 0. So we are not considering AP for that isotope, and we will just calculate. We will calculate the rest of the things here. Okay. So we will calculate the rest of the things here as a EB. Then you can see that the EB for the S1635 is 307.424 MeV. Now I have already mentioned that binding energy per nucleon, but this is for the binding energy for whole the nucleus. Then binding energy per nucleon will be what? There are how many nucleons are there? There are 35 nucleons, right? So because the AA value is 35. That means binding energy per nucleon will be EB35 divided by A. That means it will give us the binding energy per nucleon for S1635 is 878.78 MeV. Just like the previous case, the binding energy per nucleon for S1636 will be this one. So here you can see that here 1636, here A is even, and also N and Z, these both are even. That means AP will be 34 MeV. For that expression only, for calculation of the binding energy of S1636, we have to mention AP as 34 MeV, and then we have to calculate the EV value. So you can see here that in case of 1636, we have A equals to 36 and both N and Z are even, so AP will be 34 MeV. And for S equals to 1637, as 37 is odd one, that means AP will be 0, and we have to calculate EB 37 divided by A as 8.73 MeV. And again for this S1638, we can have AP equals to 34 MeV as 16 and what will be the 16 and 18, no 16 and 16, yeah, sorry 16. So I mean n equals to, sorry, z will be 16 and n will be 38 minus 16. So what will be the value? This is 22. Okay, so both are even, that means we can have AP equals to 34. We have to take the AP value non-zero, which will be 34 MeV, and putting these values for calculating EB, we can have EB 38 divided by A, which is 8.727 MeV. Now you can see that among the four of the binding energy per nucleon, 8.78, 8.83, 8.73 and 8.727. So which one is the most one, I mean largest value? The largest value is for S1636. That means the binding energy per nucleon is largest for S1636, and thus the stable, I mean most stable isotope will be 1636, which is the option number B. So for knowing the most stable isotope, we have to calculate the binding energy per nucleon for each of the isotopes, and which will give the binding energy per nucleon will be the most, I mean largest value. This isotope will be the most stable isotope among all of the isotopes. That is the main thing for that expression, I mean for that question. Okay, so now coming to the question number 5. In that question number 5, it's a very simple one question. Like let's say the question at first, the question is binding energy of deuteron is 2.2 MeV. Okay. So what is deuteron? Deuteron is heavy. See, I have already mentioned here. So deuteron is heavy hydrogen, where you can see proton and neutron. Okay. So like yes, you know that H11, H12 and H13. So this is H11 is the deuteron and this is tritium. Okay, and this is normal hydrogen. So here if I write here about the deuteron, it is given that binding energy of deuteron is 2.2 MeV, and they are asking about the frequency of the photon needed to dissociate the proton and neutron in deuteron. Okay, so in that deuteron you can see that H12, that means by seeing the notation, what I can conclude like that Z will be 1, N will be 2 minus 1, that means 1, and A will be 2. That means inside the deuteron nucleus, what is there? One proton is there and one neutron is there. The frequency of photon needed to dissociate the proton and neutron in deuteron is which? I mean how much? That we have to calculate. So from the quantum mechanics, a very similar expression is E equals to h nu. All of you already know that one. So E equals to h nu. So for that E, here E is nothing but 2.2 MeV. That means the binding energy what is present in the deuteron. So if I put here E equals to 2.2 into 10 to the power 6 eV, that means 2.2 MeV. The energy needed to dissociate P and N will be h nu, and here they are just asking about nu. What will be the value of nu? Nu will be EB divided by H, a very simple one. So if I put here the value of H, then we can have the value of nu as 5.3 into 10 to the power 20 Hertz. You can see in that question they are asking about something into 10 to the power 20 Hertz. That means we have to put only this number in that as an answer. And here they have already mentioned that what is the value of H. H is 4.136 into 10 to the power minus 50 electron volt into second. So if I just put these values, then we can have the frequency. And yeah, frequency will be on second inverse. As you can see that EB is MEV, EV, because it is 10 to the power 16, 6 is already multiplied, and then H is with 10 EV into second. So nu will be what? Nu will be EV divided by EV into second, which is nothing but second inverse and which is known as Hertz. So in that expression the frequency will be in hertz, that means second inverse, and the frequency will be 5.3 into 10 to the power 20 hertz. This is the expression, I mean this is the answer. Okay. So now coming to the second one, I mean the sixth number question. In that sixth number question, if the spin of a bound state of 1 neutron and 1 proton is measured to be 2 and it has even parity, what are the possible values of relative orbital angular momentum between the neutron and proton in this bound state? Okay, so if the spin of a bound state of 1 neutron and 1 proton, 1 neutron and 1 proton bound state means it is deuteron, right? 1, 2. 1 proton is there and 1 neutron is there. So if the spin of a bound state of 1 neutron and 1 proton is measured to be 2, the spin is 2. Okay, this spin is this one, like I will tell the difference between I and S. So and it has a even parity is even, this one is positive. What are the possible values of relative orbital angular momentum between the neutron and proton in this bound state? You can see that there are 4 options and they are asking about what are the possible values. That means it can be more than 1 also. I mean it can be 1 or it can be more than 1 also. But whatever it is given, we have to clarify the answer. So what they are asking that the relative orbital angular momentum, that means L value they are asking, and they have given well that I value and they have given that parity value. So basically what is here like I equals to S plus L, very simple one, like spin orbital momentum and angular, I mean this is angular orbital momentum and this is spin orbital momentum as a whole, this is the total angular momentum. So this they have mentioned here I as 2, right? Now I can have a value like L plus S, this value. So and this will be the quantum mechanical adding, I mean quantum mechanically it will be the addition. Okay, so the total angular momentum is the sum of orbital angular momentum and spin angular momentum S. Now they have already mentioned that H1 2 will be there, that means proton is 1 and neutron is 1. So these 2 particles are present in the nucleus, that means each and every one is the Fermi, that means they have spin half particle, right? So what will be the combined spin angular momentum of the system? The spin angular momentum can be right as I already mentioned for the first question, that S1 minus S2 to S1 plus S2 in step of 1. So this was already mentioned. So here what is the value of S1 and S2? S1 is half, S2 is half. That means the S can have the value S1 minus S2, that means 0, to S1 plus S2, that means 1 in steps of 1. So in between 0 and 1 there is nothing in steps of 1, that means capital S can have the value 0 or 1. Now coming to the 0 case, and after that we will come to the 1 case. So if S equals to 0, okay, yes, as I already mentioned, I is S plus L. That means in one condition, let's say S equals to 0 and our I is 2. That means L should have a value of 2, right? And in another condition, that S equals to 1 and our I is 2. That means for that case L will be 1. So L can have the value 2 or 1. These 2 are the possible values for orbital angular momentum for that combined system. That means L can have the value 1 or 2. But they have mentioned another condition, that the parity will be positive. So how we can have the parity will be positive? Parity is nothing but minus 1 to the power L. So if I am putting here L equals to 1, that means minus 1 to the power 1, which is minus 1, that means negative. So this L equals to 1 is not possible, as they have already mentioned that parity should be positive. Now coming to the second option. In that second option, L equals to 2, that means P will be minus 1 to the power 2, which is positive, right? So that means we can conclude that L can have the value 1 or 2, but due to the parity constraint, L will not be the value of 1, L should be the value as 2. So the answer will be L as 2, which is nothing but the answer number 3, C. Okay, so this is the answer of that question. Now coming to the seventh one. I think this is the last one, but yeah, let's see. So the seventh question. In that seventh question, the magnetic dipole moments of deuterium reveal that it is always found to be in a state with relative angular momentum of neutron and proton equal to 0. And we have to say that it is true or false. Okay, like this is the statement. This is one statement, it is given, and we have to say that this statement is true or false. What is the statement? The statement told us that magnetic moment measurement for the deuterium nucleus reveals that it is always found to be in a state with relative angular momentum of neutron and proton equal to 0. That means they are telling me about the magnetic dipole moment measurement of deuterium, that means the mu. This mu is telling me that in that deuterium H12, the neutron and proton has a combined relative angular momentum which is 0. L equals to 0. It is always, the mu, the magnetic dipole moment of deuterium is saying that L should be 0 always. This is the statement. We have to verify that statement, is it correct or not. Okay. So for that statement, what we will do, like here there is a simple expression for that magnetic moment. You can see here, as I told there, like okay. Yes, so for S equals to 1, like what was there in neutron and proton. So in neutron and proton, half and half was there. So that means as I told, like half plus half, that means it will give 1 or 0, 0 or 1. So like, and sorry, here J is the total angular momentum, which is S plus L. So for the case of there can be two options. One is L equals to 0 and another one is L equals to 2. So in that in that case, we can obtain mu will be 0.879, and for that last case we can have 0.310, and the measured value of the deuterium magnetic dipole moment seems to be 0.857 mu n, but its angular momentum has a mixed state of L equals to 0 and L equals to 2. That means, as in that statement they are asking that magnetic dipole moment of deuterium reveal always that L should be 0. This statement is 0. This statement is false, because 96% of mu is coming from L equals to 0, but 4% of mu is coming from L equals to 2, as there are two values of L. That means L can have 0 or 2. So that 0, L, from that L equals to 0 contribution, mu is coming as 96% of this value, and for 2 it is coming as 4% of the total value. That means the deuterium is a mixture of these two angular momentum 0 and 2. It is not that always L equals to 0 will be there. So the statement, whatever it is mentioned here, magnetic dipole measurements of deuterium reveal that it is always found to be in a state with relative angular momentum of neutron and proton equal to 0, that it will be a false one. The actual one will be, the magnetic dipole moment measurements of deuterium reveal that it is a mixture of 2 relative angular momentum of neutron and proton, which is L equals to 0 and 2 in the ratio of 96:4. That means 96% for L equals to 0 and 4% is for L equals to 2. So this is the answer of that question, whatever it is mentioned in the question number 7. So these were the previous year week 1 and week 0 questions, and I think we have too much time in our hand. So if you people have any questions or doubt, you can ask me, or otherwise we can go to the second week assignment also, because as you can see that these are the very simple questions and answers. So we can move on for the next week also. Like obviously there will be another session will be on next Sunday, but still, like if there is too much time, then we can discuss the second week assignment also for the previous one. But yeah, before that we have to know that all the questions are understandable by all of you. These are the very simple one, very basic of the nuclear and particle physics questions. So these are the first week assignment, so that's why these are the very simple one. So is there anyone, do you have any questions on that, or should I move on the next week? Yeah, no need to raise your hand, you can just unmute yourself and you can ask me question. No need to raise your hand, and after that you can ask me question. What is the name? Ram Babu, can you explain last question? Okay, so in that last question, yeah, so the last question is asking about one statement. Okay, in that statement, what is the question? The statement is like magnetic dipole moment of the deuterium. This magnetic dipole moment calculation tells us one conclusion, that L will be 0 always. L is the relative angular momentum, I mean total orbital angular momentum. Okay, so this is the statement. The statement tells that our magnetic dipole moment measurement of deuterium can reveal one conclusion, that L should be 0 always. This is the statement. We have to find that statement is correct or not. This is the question. Okay, now we have to find that L will be 0 always or not. This is this is our task. We have to answer on that. If L will be 0 for all the time, which will be the conclusion coming from the magnetic moment measurement of deuterium, then we can say that okay, the statement is correct. If it is not, then we can say that the statement is not correct, it is false. Okay, so for that we are doing something here. So what we are doing here, basically the calculation of that mu, we are doing the calculation of magnetic moment, right? So in that calculation of magnetic moment, see, okay, I will tell a little bit on that. Basically deuteron is a H12, and here the parity is positive always. Okay, so if parity is positive, then you can see that our L was what? L can have 0 or 2, because parity is -1 to the power L. So if L will be 0, then also it will give positive. If L will be 2, then also it is give positive value. So our L should have 0 and 2 value, but that L equals to 0, how much it is contributing to our mu calculation, or L equals to 2, how much it is contributing to our mu calculation, that is the main thing. So this is the expression for S equals to 1 and L equals to 0 state, and this is the expression for S equals to 1 and L equals to 2 state. So you can see here that mu, for the first case, mu is half into GPS plus GNS. Okay, what is G? G is nothing but the gyrometry ratio for proton and neutron. So if I put these values, then we can have a value of 0.879. So this is coming from L equals to 0 combination, right? But if I write the second combination, in that second combination you can see that S equals to 1, L equals to 0, which is give the total angular momentum as 1. From that expression we can say our mu value is 0.310. that means you can see that 0.310 is not equals to 0. That means there is a non-zero value of mu which is coming from L equals to 2 state, right? So with the help of these values, like with the help of this mu and this mu value, we can see that only L equals to 0 is not responsible for giving the total mu value. L equals to 0 and L equals to 2 is giving the total responsibility for giving the actual mu value. Mu means like magnetic moment value for deuterium. So whatever it was saying in that question, that magnetic dipole moment measurements of deuterium reveal that it is always found to be in a state with relative angular momentum of neutron and proton equal to 0, that is not correct. Angular momentum should have two contributions. One is from 0 and another one is like L equals to 2. These two angular momentum values should give us the total magnetic dipole moment of deuterium, and these two will be present in our nucleus of deuterium. It is not correct that only L equals to 0 is present in our deuterium nucleus. So this is the case for that answer. So like whatever the statement is given here, it will be false, and the ratio they have mentioned that L equals to 0 is giving our mu as 96% and L equals to 2 is giving our mu as 4%. So this 4% is a non-zero, right? This is not a 0%. That means our L equals to 0 is not the full responsible for giving mu. L equals to 2 is also giving us mu value. So this is a mixed value. This is a mixed orbital angular momentum of L equals to 0 and L equals to 2. As I think I have already mentioned, yes, its angular momentum has a mixed state of L equals to 0 and L equals to 2. So L equals to 0 is about 96% and L equals to 2 is giving about 4% of total magnetic moment of deuterium. So this is the 7th question, and yeah, this is the 6th one. 6th one is also simple. You can ask any question, whoever raised the hand. Rambabu, yeah. You can unmute yourself and you can ask me the question, or you can give it to the chat box also. Where is the chat box? Let me check the chat box. I shared a jam file with the meeting. What will be with the jam file? Can you explain? Lalit Kishore. Should I write on that jam board? Jam file? Okay. Okay, so as I think there is no other questions, you can ask me any other questions if you want, like among that questions, or otherwise should we move to the second week? I think for the second week it will be a little bit tricky, not that much tricky, but it will be a little more tricky as it is second week. So I think I should go to the second week or not. Okay, just go. I'm just going through a very simple questions on second week, and after that we will move to the, I mean in that second week also we will do the same thing, but just little bit, just little bit of questions, not answer I will tell. That may be a good one. So okay, nuclear cell model I have to not to tell you, otherwise you can't say that. Okay, the question was like, what is the expected spin value of ground state of the nucleus nitrogen 715 within the nuclear cell model? That is a question. Okay, so like we will not discuss about the nuclear cell model this week. We will tell in the next week. Okay, I will not tell you the answer on that. Then what is the expected parity of the ground state of the nucleus? Then in the next question, So in the next question, what is the expected parity of the ground state of the nucleus silicon 1429 in cell model? It is even or odd. That type of questions is there. And then coming to the third one, in that okay, so all the questions are basically based on the nucleus cell model. Within the nucleus cell model, spin and parity of the first two excited states of magnesium 1225 are, what is the value of spin and parity for the magnesium 1225 for the first two excited states, they are asking. Okay, so I will not tell about these things. Okay, now the next one was consider the classical case of a particle of mass m and charge atom moving in a circle with angular momentum this. Magnetic dipole moment associated with this is, I think you can do that one right now also. It's a very simple one. There is nothing with the nuclear cell model and nuclear particle physics actually itself. So okay, we will tell that also. And that fifth question, in a scattering of electron of a nucleus, electrons of energy these are used. If these electrons are represented by a wave function where the position coordinate is along z axis, what is the value of k? That is also not required for the then the next question is, okay, the next question is this one. This is also not required about the nucleus cell model, so we can discuss these questions also. An experimental measurement of the orbital angular momentum of deuteron, that mass samples were selected, approximately how many of them would have measured I equals to 2 into h by 2 pi. That type of questions are there, like what will be the value of how many of them would have the measured I. So these are the questions. So what should I do? Should I explain? Okay, I think we can calculate this thing, question number 4, because there is nothing with that cell model and all. It's a very simple one. Let me do that one. Answer, no, which one? This one. Okay, so consider the classical case of a particle. Here what they are mentioning, see this is nothing with that cell model or week 2 lectures and all, so that we can do that one, no problem on that. Okay, so what is the classical case? The classical case of a particle of mass is 1 into 10 to the power minus 30 kg, it is given, and the charge is, that the Q is 1.6 into the most stable isotopes, minimum binding energy and maximum binding energy plus nucleon. Please clear this down. Most stable isotope means maximum binding energy per nucleon. Okay, by maximum binding energy means like we have to give more energy to tear up. That is the thing. You can say in this way also. So most stable means if there is if there is the maximum binding energy per nucleon, that means we have to give more power, more energy to tear up the nucleons from the nucleus. That means this is a most stable one. If the minimum binding energy is present in that nucleus, that means it is the least stable isotope. Stable means like, stable is what? Stable means like, most stable means we have to give more heat to, more energy to tear up the nucleons. So obviously when the maximum binding energy per nucleon will be largest, that means that binding energy per nucleon will be maximum. At that condition only we can have the most stable isotope. Okay, like binding energy is nothing but, in this situation you can say binding energy is nothing but the energy that need to tear up the nucleons from the nucleus. So most binding energy means, maximum binding energy means we have to provide more heat to, more energy to that nucleus. That means it is a most stable isotope. Most stable means obviously we have to give more energy. If it is a least stable, that means it can easily tear up the nucleons from that nucleus. So whenever they are asking about the most stable isotope, we have to consider the maximum binding energy per nucleon. Is it clear or not? So most stable is maximum binding energy per nucleon. Least stable, if they are asking, then minimum binding energy per nucleon. Okay. So binding energy means binding energy. I mean like how much we can have the energy to bind, or reversely we can tell that how much energy we have to give to tear up the nucleons from the nucleus. That is the thing. You can see that like for the for the noble gases, they are the most stable particles, right? They are the most stable elements. So in the noble gases we can have the most binding energies. So I mean that's why they are noble. I mean noble gas means like they are not interacting with anyone very much, but obviously it is in chemical reaction condition I am talking about. But in the nucleus itself also we can have that very similar like thing, that if there is a most stable most binding energy is there, maximum binding energy is there, that means it is the most stable isotope. If it have a least binding energy, that means it is a least stable. Okay. So yeah, so what I was talking, yes. Oh sorry, what I was, yeah. So here you can see that the classical case, for the classical case of a particle of mass this, the charge is q equals to 1.6 into 10 to the power minus 19 coulomb, right? And moving in a circle with angular momentum, L is given as 2 into 10 to the power minus 34 joule into second. Then they are asking about the magnetic dipole moment associated with it. What will be the magnetic dipole moment, which is nothing but mu value. So just simple one, like if there is a classical charge particle, then we can have mu is half q v r. So q is there already given. Now we have to calculate what is the v and r. V and r they are not giving directly. So what we will do? We will like do here, q will do, then m v r we will just multiply m here, and then we will just divide m, two dimensionally correct that one, as well as the mathematical collection is there. So half q is the charge, and then m v r is nothing but the L for the classical particle. Just mention that this is a classical particle. So half q, L is m v r, then divided by m. So if I put m value, L value, q value, then we can have the mu value, which is 1.6 into 10 to the power minus 23 ampere meter square. Just careful about the unit. What is the unit for that? I think they have already mentioned here. Yes, they have mentioned here ampere into meter square. We have to calculate that one in ampere into meter square. So q is in coulomb, L is in joule into second, m is in kg. So we have to calculate in that way, so that we can have ampere into meter square unit for that mu value calculation. And this is not, I already told na, so this does not have any relation with the nuclear and particle physics. It is totally based on the classical mechanics, right? In that classical mechanics, the magnetic moment is half q v r if a charged particle is there in a circular orbit, then half q v r, then we are just multiplying by m and then divided by m, then q L divided by 2m, then L is, we are just putting L value, q value, m value, then we are getting mu value, magnetic dipole moment, which is 1.6 into the minus 23 ampere into meter square. I think this is fine. This also we can do, but yeah, we will do in the next class, or we can do right now also. Oh sorry, this is the question. This is also not directly related to the nuclear and particle physics course. This is directly related to the quantum mechanics course. As I have told that this is related to the classical mechanics, this is related to quantum mechanics course. As you can see that the angular wave function is given here, and they are just asking for the k value. So I mean, very simply, like, we have to just put the energy value, then we can have the k value from that. Okay, let's do that one also. So this expression, this question is obviously not related to nuclear and particle physics, so we can do that one also. So what is the question? In a scattering of electron of a nucleus, okay, I mean scattering of electron of a nucleus, one nucleus is there and one electron is going to scattered off from that. The electrons of energy, electron has a energy E will be 10 MeV. If these electrons are represented by the wave function is phi equals to a e to the power I k z, where the position coordinate is along z axis, the position is along z axis. The value of k is what? Okay, this is the very simple, like, as they have already mentioned that the electrons are in wave function, that means it is, we have to consider the quantum mechanical calculation for the electron. So for the quantum mechanical calculation, E is what is the value of E? E as the h bar square k square divided by 2m. So this expression is nothing related to the nuclear particle physics, right? It is totally based on the quantum mechanics. So if I just put here k value, like, okay, so they are asking about k value, and we know m value for electron, we know the value of E. So, and obviously we know the value of h bar also. H bar is nothing but h by, h bar is h by 2 pi. So if I put these values, then we can have k value. K will be what? K will be 2me divided by h bar square. So E is in MeV, I think MeV it was, right? Yes, E is in MeV, and m we can have in MeV also. For electron, what will be the value of m? For electron, m will be 0.511. What? MeV or KeV? MeV. Okay. So just put these values here. 0.511. Then yes. Okay, and in MeV to EV we can just convert here. Then it's 10 into 10 to the power 6 EV, and then h bar is given there. Yeah. So if I just put the h bar value here, then we can have one expression for the k. K is 1.61 into 10 to the power 13 meter inverse. Just careful about the unit so that we can have the correct one. You can see that the correct value is 1.6 into 10 to the power 13, and it is already given in the meter inverse unit. So we can have the expression of C. Just putting the expression that E equals to h bar square k square divided by 2m, we can have the k values. And we are just going to put E value and m value, then we can have the k value here. Okay, so this is the question number 5, and okay, these things we will tell later. Okay, so among these 3 weeks, I mean obviously we have to focus on these 2 at least, week 1 and week 0. Among these week 1 and week 0 questions, if you have any doubt, you can ask me. I'm just scrolling down again so that you can have the idea that what were the questions. So this is the H1 and H2 question, H1 minus H2 to H1 plus H2. Then the second one is the excited state of energy, from how much to how much they are jumping, and how much energy is released from that. Then in that question number 3, what is the which force is the reason for the nuclear stability? Gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force, and it should be with strong nuclear force. Then the fourth question was like radius of the nucleus. What will be the radius of the nucleus for phosphorus? 1531. Then okay, this is the mass of proton and neutron, and for the binding, find the binding energy of that fluorine 919, and there is something given like mass of the fluorine is this one, so we have to take the answer in MeV. So this is the expression for that. Now coming to the first week. In that first week I have already mentioned that one. Yes, P1531. Then this one is the binding energy calculation with the help of semi-empirical mass formula. The first one was the very simple one that we are just going to subtract two values. One is the mass value and another one is the nucleon mass. So we are just going to subtract that one. With the help of that expression we can have the binding energy. Otherwise semi-empirical mass formula is also there for calculating binding energy. So this is the expression for the semi-empirical mass formula, and here AV, AS, SE, asymmetry, AP I have already mentioned. AV is for volume correction, AS is for surface correction, AC is for Coulomb correction, A asymmetry is for asymmetric correction, AP is for pairing correction. And then we have to mention, we have to be careful of that AP values also. As you can see that A is 60 and Z equals to 28. If Z equals to 28, that means I think I have already mentioned here N equals to 32. Yes, that means both are even number. That means obviously AP will be positive. Positive 34 MeV. Then the third question was the same one. The fourth question is the most stable isotope among the following. So we have to find which one is the most stable isotope among these one, and for that we have to just calculate the binding energy for each of the isotopes, and we can have the binding energy per nucleon. Okay, then which one has the binding energy per nucleon as the greatest value, the largest value? This will be the most stable isotope. Now coming to the fifth one. The fifth one is the binding energy of deuterium is given, and we have to calculate the frequency of the photon needed to dissociate the proton and the neutron in deuterium. So for that we just have the simple relation as equals to H nu, and E here E is the EB, that means the binding energy of deuterium, and just putting the values of that EB equals to H nu, we can have the value of nu. After putting the value of H, we can have the value of nu. Now in the sixth question, they were asking me that if the spin of a bound state of one neutron and one proton is measured to be 2 and it has the even parity, what are the possible values of relative orbital angular momentum between the neutron and proton in this bound state? So as there are two constants given, one constant is like total angular momentum is 2, and another constant is parity is even. So with the help of these two conditions, we can have L equals to 2 will be there. Relative orbital angular momentum will be 2. There was another option also which was 1, I think, yes, which was 1, but as parity is even here, that means obviously L should be 2, because minus 1 to the power L is positive. So if L equals to 1, then minus 1 to the power 1 means minus 1, that will be negative. But if L equals to 2, that means minus 1 to the power 2, that is positive value. Now in the next question, they were asking about the magnetic dipole moment of deuterium. It is found to be in the state of the relative angular momentum of neutron and proton equals to 0. But it is true or false? It will be false, because there is a 96% of magnetic moment is coming from L equals to 0 state, and from 4% of magnetic moment, 4% of magnetic moment of deuterium is coming from the L equals to 2 state. So the statement which is telling that L equals to 0 is the main reason for calculating magnetic dipole moment is wrong. It is false. Okay, these are the questions, and then we were also discussed about this first, two questions of the next week. This one and other one was, yes, this one. Okay. So this one they were asking about the mass of the particle, and charge of the particle is already given. In a circle the charge particle is moving with the angular momentum this one. Then what will be the magnetic dipole moment? So magnetic dipole moment is half q v r. Then we are just multiplying this with m v r q by m. Then m here is orbital angular momentum as L. Then it will give us L by m into q. So just putting the values of q, L and m, we can have the magnetic dipole moment. So these are the simple one. And then in the next question it was telling that energy is this one, and these electrons are represented by the wave function. If energy is given, then what will be the value of wave number, which is k. So the expression is E equals to h bar square k square by 2m. Then from that expression we can have the k value root over 2m e by h bar square. Now putting all the parameters a, m, e and h bar, we can have the value of k, which is nothing but 1.5 into 10 to the power 20, no, 1.6 into 10 to the power 30. This one is the right answer, not this one. So this one is the right answer, 1.61 into 10 to the power 13. Yes, this one. So the correct answer will be B. So these are the like week 1 and week 0 questions, and some of the questions from the week 2 questions. These are obviously the previous year questions. Don't like merge it with the this year question. This year question will be different, but obviously it will be very similar to the week 0 and week 1 of the previous year question. So if you have any doubt, you can ask me, or otherwise okay, someone is okay. Yeah, sure. We were discussing about week 0 and week 1 questions, previous year assignment questions. Okay. From the next class onwards, I think we have to put more questions on that, because as it is a 2 hours question and answer discussion. So we think we have to add some more questions on that, so that the time will be covered. I think I will give some more questions, and let's say like from the next week onwards, I can give you the questions as a homework also, or you can do right now also, like that it can be possible, so that the time will be covered. Otherwise you can see that these questions are very not very simple, but yeah, like little bit simple, so that it can be over by half an hour or 1.5 hours at least, at most. So yeah, and from the next week onwards I will give some extra questions on that, not only the previous year assignment question. After that also I will give some more extra questions, so that we have to solve these questions by that time period, and it will be helpful for both of you, I mean all of you, so that it will be good. And I think I will cover basically whatever sir is teaching there in his lecture. So according to that one, I will prepare some questions, and we will discuss on that next class. Okay. I think there is nothing more than that, so that we can leave the meeting today, and we can have the next class I think next Sunday. Yeah, next Sunday. Someone is asking something. Yeah, see, whoever raised their hand, don't raise the hand. You can just unmute yourself and ask my question. Okay, there is no need to raise your hand. You can ask me, you can unmute yourself and raise the ask the question. Whoever
Good evening, ma'am.
Yeah, I can hear you.
Hello, good evening, ma'am. Hello, good evening, ma'am.
Yes.
Muhammad wants to ask some question.
Yes.
Voice is audible, ma'am.
Sorry, I can't hear you. Sorry.
Voice is audible, ma'am.
Yes.
Which text reference is suitable for paper nuclear and particle physics book, ma'am?
Okay, reference.
Yes, ma'am.
For the references, you can just follow. First of all, you have to follow sir's lecture. Okay, so whatever sir
Okay.
is teaching there in that weekly basis, you have to follow that one sir's lecture. That is very much useful. And
Okay.
in addition of that, I can prefer you for particle and nuclear and particle physics as a very basic thing. There is one like Peskin's book was there, and then okay. Uh, mm, Peskin book is there, Griffith's book is there, and then but that will be very much high standard for you people. But as per I think Peskin's book is there. Peskin's book you can follow, and Griffith's book on particle physics is there specifically. You can follow that one also, and then. Another one was there, one Indian guy was there. I forgot his name.
SN Ghoshal. SN
Yes,
Ghoshal.
yes. Asian
Nuclear
Ghoshal.
physics.
Yes, thank you. Asian Ghoshal book was very nice. So Asian Ghoshal book you can prefer that one. Yes, thank you. So Asian Ghoshal
Okay,
you
ma'am.
can go for.
Thank you, ma'am. Thank you, ma'am.
We'll get these
Ma'am.
slides. Yeah, Ria, I can tell you that whatever the slides are there. Okay, let me see.
Hello, ma'am. This is
Just a
Dr.
minute.
Sugandha.
Just a minute. Actually, someone asked me one question in chat box. After that, I will go with you. Okay.
Okay.
So,
No problem.
Ria, I can tell you that whatever the slides are there, whatever I am just showing here right now, these slides as well as the lecture, all the things will be uploaded. I think one Google Drive or something. It will be there, and you can have the access of that also. Like the NPTEL coordinator will send you the details. Okay. And one more thing is that the recording, whatever it is there, it will be uploaded in the YouTube channel, and they will share the YouTube channel link with all of you. Okay, now you can just tell me what was the question. Who was
Hello, ma'am.
yeah.
Here I am teaching the nuclear and particle physics for NSC semester 4 in Nagpur University.
Okay.
For PG, nuclear and particle physics. For this, I refer the SN Ghoshal book, but I do not get any Indian author book for the particle physics specifically. So, if you know this, that is the any Indian author book for particle physics, then kindly suggest me.
Pal, PB Pal, Palasbaran Pal. Palasbaran Pal is good.
Okay, write in chat box now, so that I will take screenshot.
Yeah, actually I don't know the name, I mean the name of that book, but you can just search particle physics by Palasbaran Pal. Okay. Palash.
Yeah, Nitin Baba's phone.
Pal. I think that is the spelling. Yeah, Palasbaran Pal. PB Pal basically. So if you just search here, you can have one thing. But SN Ghoshal is very much good. Like when we were in that BSc level things, that we have already read that one, and it was really nice. And for that pace, I mean for the advanced level, as you told that you are teaching in PG. So for the advanced level for the particle physics, I would recommend that Griffith's book. Griffith's book is very much good for the particle physics, and also that Peskin book is good. Then Perkins book is also there. One is Perkins book is there. Then Crane's book is there. So these books are good. Like these are the not Indian authors; they are the foreigner authors. But yeah, they are good.
Okay, ma'am. Thank you.
Ram Babu, you can tell me. You can just unmute yourself. No problem on that. Don't raise your hand. Just unmute yourself and you can ask me the question. Ram Babu, do you have any question? Or you can, if there is any problem with your mic, then you can just write in the chat box. We can discuss that.
Hello, ma'am.
Yes.
What about DC Thayal book? DC Thayal.
DC Thayal. I have not heard that. Maybe it will be good, but I don't know. Sorry.
Okay, ma'am. Okay, thank you.
I mean, is it Indian author or something?
Indian author, DC Tayal.
Okay.
Or what about SB Patel? What about SB Patel?
Yeah, SB Patel is there, but I have not heard about Thayal or what. No, I have not heard that.
Okay.
Yeah.
Okay, man. Thank you. Thank you.
Yes, like standard book means like these books only, like Crane's book, Griffith's book, and then Parkin's book, Peskin's book. Peskin's book is little bit advanced, more advanced, but Parkin's book is good. And obviously, as a Indian author, Polas Pal is there, and then S.N. Ghoshal is there. S.N. Ghoshal book is very much useful. For the first, I mean that simple level, basic level things.
Um, what what is the book for net level? CSR net level.
CSI or net level. Okay. See, basically in CSI and net level, what we need to do? We need to do the basic things, right? I mean, what for the if you are asking me about the specific chapter of that things like nuclear and particle physics only, for the nuclear and particle physics, you have to do the basic things at least, because you can see that in CSI or net exam there is not that much questions are coming from nuclear and particle physics. Whatever it is coming from nuclear and particle physics, that are not that much high level questions. Okay, so these are very basic level questions, like in the cell model what will be the nuclear, like ground state, then this type of questions are mostly coming. So for that I would suggest, I mean only for the nuclear and particle physics topic I would suggest that simple S.N. Ghoshal book is enough, or something like Peskin book or Griffith's book is good. But yeah, I mean for the other topics you have to go little bit more detail. But for nuclear and particle physics, if you can check last 5 year or 10 years question paper of CSIR net, you can see that for nuclear and particle physics there is a very less number of questions. I mean at most you can see like 10 to 15 marks for this topic, and this is whatever it is coming, it is a very simple one. So for nuclear and particle physics you can use any type of book.
Okay, madam. Okay, thank you. Thank you.
It's a very simple one, you can use any type of books.
Okay, madam. Thank you.
So any questions so far? About the you can also ask me, see, as basically this class is about 2 hours, so as I already told you that only the question answer will be, I mean only question and answer and discussions will take at most 1 hour, let's say, but next 1 hour we have to do something, right? So if anything has a doubt on that, any theory part also, you can tell me about that one also. I want to try, I can try that one to explain you. So as a theory part also, if there is any problem, if there is any issue on that theory part, what is sir is teaching there in that lecture, obviously sir is teaching very well, so you can understand all of most of the things from there. But if still something is missing there, then you can ask me, I can tell you in that in this question also. Both DC Tawar and SP Patel are enough for college examinations, they do not go much in depth. Okay. Someone has already mentioned that these two books, Ashwin Nayar, DC Tawal and SP Patel. I don't know about DC Tawal, but yeah, SP Patel I have heard, but I don't know about DC Tawal. Okay, thank you Ashwin. It is already mentioned that they do not go much in depth. Okay. In S.N. Ghoshal, I can tell you that they are giving in a very simple manner. Okay, they are giving in a very simple manner, and as a very beginner of the nuclear and particle physics, it is the best one. Not that much high level, but yeah, as a very beginner, you can see that. Okay, so if there is anything in the theory part when you are going through the whole lecture and whole the course of nuclear and particle physics, You have some doubt on that theory part also, you can just mention, like let's say you are mentioning this week, and we don't have to discuss this week, we will discuss in the next week. So like that we can discuss. So it's totally up to us, like obviously the you people and how we are interacting, that will be the important thing. So whatever will be your improvement, your benefit, we will do that one. And for Palas Baranpal, I will suggest you that Palas Baranpal is good, but yeah, it's a little bit advanced level than SN Gosha. Okay, so I think there is not that much question and answer till now. So we can leave and we will meet in next week. The same time, 3 to 5. Okay. I think we can stop presenting. Is there any other questions to all of you? Is there any other question? I think no. Okay, so we will meet in the next class. Okay, bye bye. Bye everyone.